Hello and welcome back to my channel, as it were, and today we're going to be looking at an introduction to power sums in the interests of solving a difficult power sums problem next week. So, first of all, what on earth is a power sum? Well, a power sum, denoted pk, of terms x1, x2, all the way to xn, these are just n terms, will be equal to x1 to the power of k plus the second term, x2 to the power of k, plus all the way to xn to the power of k. This can also be written as the sum. That's what this sigma means, this capital sigma, the sum from I equals 1 to n of xi to the k. So let's say we had terms x, y, and z, so x1 equals x, x2 equals y, x3 equals z, and we were looking at pk of x1, x2, and x3, we would have x to the k plus y to the k plus z to the k. And that would be our power sum. The next thing we need to know is we need to know the elementary symmetric polynomials. And what these are the makings of the polynomial. So in roots of polynomials topic in further maths, we talk about how different formations of the roots can make up the different coefficients. So for example, we have ax squared plus bx plus c has roots alpha, I'm going to rewrite that again in red, alpha and beta, and we need to find a way to arrange these different coefficients in terms of alpha and beta. Well, so the first term will be a, or the first thing we do when we're working with these is we divide through by a, and so what we have is x squared plus b over a x plus c over a. And it turns out, which is a useful phrase, which means I'm not going to show you why, but it turns out that this is actually equal to x squared minus alpha plus beta x plus alpha beta. So the sum of the roots, the negative sum of the roots is equal to b over a, and the product of the roots is equal to c over a. But that's a similar idea, and hopefully that will get you to understand what these are. So E0, denoted with an E and a little 0, of our terms x1, x2, all the way to xn, is always equal to 1. It is the identity elementary polynomial. It is the identity elementary symmetric polynomial. Next we have E1, which is just your base sum of the roots, or sum of your variables. So of these terms, it is equal to x1 plus x2 plus x3, etc., all the way to plus xn. And that, of course, is equal to the sum for all x up from 1 to n. That's what it equal to in sigma notation, and that will usually, so if we look at a polynomial, I will give you an example of this later, of where this applies to sum of roots and that sort of thing. Then we have E2, which is equal E2 of, I've got to write this, it's just more correct if I write it that way. E2, which is the sum of paired roots, so you have your x1, x2 plus x2, x3, it doesn't have to be in that order, but the sum of all paired roots. And well, that's what it's equal. It's the sum of all paired roots. Then we have E3, which is the sum of all tried roots, and so on after that. The next thing we have to deal with is E of n, where n is the number of terms, will always be equal to the product of the roots, so x1, x2, xn. It will always be equal to the product of the roots. And ER is the final one we have to be aware of. ER is equal to 0 because R is greater than n. So if R is greater than n, ER will equal 0. So let's say we were dealing with 3 terms, so x1, x2, and x3. E of 4 would be equal to 0. To explain this better, I'm going to deal with a polynomial f of x. So f of x is equal to x to the n plus the coefficient a n minus 1, x to the n minus 1 plus a n minus 2, x to the n minus 2, and so on. And that can be factorised as x minus alpha x minus beta x minus gamma, and so on until we have the right number of terms. I'm just going to change that to black because it looks neater. And so on until we have the right number of terms. And that's how we factorise it, and that can also be written as x to the n minus, this is where the colours come in, minus E1 x to the n minus 1 plus E2 x to the n minus 2, and so on until we get to plus minus 1 to the n times En. And let's substitute in the roots alpha, beta, and gamma and sum them all together. And as we know that from factor theorem, if we f of x, where if we do f of a root, that will always be equal to 0. So the sum of all these things will be equal to 0. So I can say that 0 equals the sum of Pn minus E1 Pn minus 1 plus all the way to plus minus 1 to the n times by En times by n. And that's what they sum to. And finally, the last thing I need you to learn for this video before we tackle the problem in next video will be Girard-Newton identity. So they said that K times by EK would be equal to ek minus 1, ek minus 1 times p1 plus ek minus 2 times p2, and so on, all the way to minus 1 to the power of k minus 1 times by e0, which we also know is 1, times by pk. And that is the Girard-Newton identity, which we will be using in next video. Thank you for attending this video of an introduction to power sums, and I look forward to seeing you all next time.